Well, good morning, and thank you very much for the opportunity to be here. Well, I'm going to speak about archetypal analysis, that is an unsupervised tool that is not very well known. Well, I'm also from Jaume University, Jaume I University, and here you have my contact. The slides are also available at my webpage. Well, this is the outline of the presentation. First, I'm going to talk about what archetypal analysis is. I'm going to say it very fast because the time is short. About archetypal analysis in multivariate data, we will see some application, and we also see that archetypal analysis can be applied in other kind of data. We will also see some derived methodologies, more application, and we will finish with the future work. Well, first of all, what an archetype is? Well, according with Wikipedia, is an original pattern from which copies are made. In real world, archetypes, we can see here some examples. For example, here we have Dr. House, and we can think that Dr. House is a mixture of 20% a doctor, 30% a detective, and 50% short temper, mala leche in Spanish. But this concept is understood by any people. In fact, this is an example of my 10 years old child. Okay, archetype concept in statistics is the same as in the life common. Archetype analysis was defined by Adele Calder and Leo Brayman 30 years ago, and they are also the same developers of random forest. The objective of archetypal analysis is to find a few, but not necessarily observe, this is important, extremal cases or pure type that are called the archetypes, in such a way that all the observations are approximated by convex combination, but mixture of the archetypes, and at the same time, all the archetypes are convex combination, mixture, they are expressed as percentages of observation. This makes very easy to understand, easy to interpret it. Here we have an example of archetypes in 2D. And we can see the differences between archetypal analysis and K-means. We have the results for 2, 4, and 8 archetypes, and 8 prototypes. With K-means, we have the representatives in the middle of the cloud. But with archetype, we have the representative points on the boundary of the convex pool, Then we have, once we have the archetypes, we approximate the rest of points as a convex combination of the archetypes. For example, if we have 3 archetypes in red, we have the points inside the convex pools generated by these archetypes are approximated exactly, and the other are projected into this convex pool. Well, here we have a variant of archetype analysis, that is archetypoid analysis, that was defined nearly 10 years ago. And the objective is to find a few, but now observe extremal cases of prototype that are called archetypoids. The points are the same. All the observations are approximated by this mixture of archetypoids, but now the archetypoids are real observations, because in some problems we want exact cases. Here we can see also the interpretation and the differences between archetypal analysis and K-means. For example, well, because humans understand better the extremes than the averages. Imagine that we have 2 features, 2 variables. One is empathy and the other one is honesty. If we apply archetypal analysis with K equal to 3, with 3 archetypes or archetypoids, we obtain this point here that is a person with high honesty and high empathy, a person here that it has high honesty but low empathy, and a person here that has high empathy but low honesty. But if we apply k-means, because many times k-means is used for segmenting of even if we don't have clusters, we obtain these 3 points in green that they are not so separated as the archetypes, and they are not so easy to understand, in the sense that they are more, they are closer, no? They are more, they are averages. So how to find archetypal analysis? First of all, with multivariate data. Let X be times M matrix with N observation and M variables or features, and the objective of archetypal analysis is to find the matrix set of k m-dimensional archetypes. Then archetypal analysis computes 2 matrices, alpha and beta, that minimize this error. X are the data, and we want to approximate this data by a mixture of the archetypes. At the same time, the archetype set are mixture of the data. This is a continuous optimization problem, and the archetypoid analysis is the same, but in this second constraint, the beta values can only take two possible values, 0 or 1, because we only we want to obtain real cases. So here we have mixed integer optimization problem. Okay, what is the relationship between archetypal analysis and other unsupervised methods? Well, archetypal analysis is in the middle between principal component analysis and k-means, if we think in this kind of tools as matrix factorization tools. In the sense that, for example, principal component analysis has no constraints about the values of beta and alpha. And they are more flexible, but the component principal analysis are not so easily interpretable. On the other hand, k-means, well, the representative points of k-means are very easy to understand, but it's not so flexible as can be archetypal analysis. Well, for finding archetypal analysis solution, Calder and Brayman proposed an alternative magnetizing algorithm that was implemented in the R package archetypes. And now this is a very active field, because they have been proposed another efficient alternative algorithm for computing archetypal analysis. There are some of them. This is in a Python library of our group. And for finding the archetypoid analysis solution, we propose an algorithm with 2 phases. One of them is finding an initial set of archetypoids, and then in the other phase, we want to improve the set of archetypoids. This also implemented in the R package anthropometry and the other methods for big data sets. I'm going to jump things because of the time. Well, where are the archetypes and archetypes located? If we have, if we consider only one archetype, then the archetype is equal to the mean and equal to medoid in the case of archetypoid analysis. And for k greater than 1, the archetypes are on the boundary of the convex hull of the data. This is not necessarily the case for archetypes, but they are also extreme cases. And which case we should consider? Well, this is the $1 million question. It's the same question that as in clustering. There are several criteria, but for example, this simple criterion, the elbow criterion, is quite practical. No? We can compute different archetypes and the error, and we can see where the elbow is found. No? Is found. Well, this is an example of archetypal analysis application. In fact, this was the problem that was the origin of because of that problem, I began to work in this area. This problem was of the Valencian Biomechanical Institute here in the Politecnica Valencia, and they wanted to design archive keys, and we consider six variables. And the point is that we wanted to obtain the extreme cases because the extreme pilots, because if we achieve to obtain a design that fit these extreme body types, then the other pilot not so extreme, then will be well accommodated. So after some transformation, we apply archetypal analysis. We consider 7 archetypes. One of them was with high percentiles in all variables. Other pilot have low percentiles in all variables, and there are more combinations. And I want to highlight this one because this pilot with high percentiles in all variables except arm was not able to be recovered with principal component analysis and consider the more extreme scores, because the objective of principal component analysis is not obtaining extreme cases. So I want to highlight this T-Rex pilot and could not be recovered with principal component analysis, but only with archetypal analysis. And as said before, we gave the extreme cases to the designer, and then the cupcake could be designed. And then we have applied archetypal analysis to different fields. For example, here's a toy example in sport analytics. Here we have the 5 archetypoid analysis of the Spanish Football League, masculine, and we have the rest of teams expressed as a mixture of these extreme teams. We have also applied archetypal analysis in texture segmentation, obtaining better results than using clustering. And as I said before, we can apply archetypal analysis with other kind of data. Here we have an example with functional data, where data are functions. I'm going to jump to all of this on the mathematical part. I'm going to show up an application. Imagine that we want to describe the countries in the world with 2 indicators, total fertility rate and life expectancy at birth during these years. There are time series. So we applied archetypoid analysis because we wanted exact countries with five archetypoids. And we have these archetypoids: Lesotho, Channel Island, Niger, Qatar, Bhutan. They have the description. I know to enter here in the description of the countries, but the point is that we can represent the rest of countries of the world with these 5 as a percentage of these 5 archetypoid extreme countries. So this is very easy to understand for non-expert persons. And the other, for example, here we have Turkey is a mixture between 30% Channel Island, 20% Qatar, and 50% Bhutan. I have not explained the description of these countries, but they are extreme in this kind of series. Of course, the point is that archetypal analysis, as they look for extremes, is sensitive to layers. So we also define a robust archetypal analysis, changing the objective function. And in fact, we also take advantage of this and use archetypal analysis to detect all layers. In fact, we obtain very good results with different benchmarks with a comparison with 23 methods. And as I said before, we have, we and other people have defined archetypal analysis in other kind of data with landmarks. We know that safe space is not a vectorial space with cars, with missing data. And then we use that in collaborative filtering technique. Morten Morov has also proposed kernel archetypal analysis, etc. With binary data, with ordinal data. And our last contribution has been defining bi-archetypal analysis. In this case, we obtain archetypal both from the observation and the features at the same time. This offers advantages over big clustering. In fact, this is a very, it was accepted last month. It's a very recent contribution, and it was published in this very important journal. As said before, there are more applications. Well, this is a very few, because there are a lot. Biology, engineering, equality, medicine, neuroscience. And well, our actual work is we have defined archetypal analysis with tensor data. This is part of the thesis of Aleix Alcácer that will be defended on September at Jaume I University, and all of you are invited. And we are also carrying on a survey with Morten Orup and Adel Kaller. Well, as I said before, there are many open questions in this field because it's quite new. And the point is everything done with clustering can be moved to archetypal analysis. And there are many open questions. Well, here are the references commented in the presentation, and all the paper and software are available at my webpage. Thank you very much for your attention. So
they use hyperspectral cameras on satellites.
Yes.
One thing they try to do is to find what they call end members,
Hmm.
which would be the same as archetypes.
Yes.
Such that all the other spectra are convex combinations, and there are algorithms that are developed in that community for trying to discover them. So it sounds like the same thing, but I don't know how to.
No. Archetypal analysis has been used for obtaining the end members, but in that imagine we didn't make that. We make segmentation of texture segmentation. It's different. But other authors have used archetypal analysis with some variation, with some depth, for obtaining the end members. Yes. I don't know if I have put that in the application, but yes, this is a very clear application. I didn't put that because, but yes.
To the letter N in the alphabet. That would be a remote sense, it would be an R.
Yes, we haven't, yeah.